Okay, welcome year 10 physics. So today we're continuing on with our electromagnetism unit and we're moving on to transformers. So transformers basically they can change voltage. They transform voltage and current is what they do. So let's explain this a little better. First of all, before we get into transformers, we have to realize that they work on two main principles, and that is this. One, electric currents produce magnetic fields. Anytime you have an electric current, you have a magnetic field present. That's how an electromagnet works, for example. So that's one thing. The other is that a changing magnetic field will induce a current in a circuit. So those are the two things. Remember, anytime you have a current, you have a magnetic field. And anytime you have a piece of wire that's cutting field lines, so you have a changing magnetic field, that can induce a current. So those are it. Currents produce magnetic fields, but also magnetic fields can produce currents. All right, so let's see here. Okay, so everybody's seen something like this. You all have these little devices to charge your phones. And what's inside of these devices that charge your phones? Well, there's a transformer inside of these. Because these turn, if you plug these into your wall has about 240 volts. But these will turn those 240 volts into about 9 volts to charge your phone. Because if you put 240 volts through your phone, it would fry your phone. So we should also mention these things also have a rectifier in them, which turns AC current into DC current. Because if you want to charge something, you need to use DC current. But we don't really care about these rectifiers right now. We're just concerned with the fact that they have a transformer in them. So that is one thing. Now, I'm sure that you also recognize, probably also recognize a transformer like this. So this would be a transformer for your computer. And these just do the same thing. So these transformers would turn 240 volts from your wall into about maybe 20 volts for your computer. Okay, so these also have a rectifier, but again, we don't care about the rectifier. We just care about the fact that they have a transformer in them to transform the voltage and the current. More on that in a second. Okay, so the components of a transformer. What is a transformer composed of? So here we have a very simple looking transformer. And we can see that the components of a transformer are, transformers have a primary coil, they have a secondary coil, and they have an iron core. So basically those are the three components of a transformer: a primary coil, a secondary coil, and an iron core. So now what do all these things do? Notice the primary coil is connected to an AC power supply. Transformers have to be connected to an AC power supply, otherwise they just won't work, because they need an alternating current so that they can have an alternating magnetic field around this primary coil. Okay, so far we have a primary coil connected to an AC power supply. We have a secondary coil that's not connected to any power supply. This secondary coil would just, let's make a very simple example. This might just have a light bulb on it. So notice there's no power supply here. It's getting all of its energy from the primary coil somehow. We'll explain how this works in a second. And one thing I just want to point out, this iron core in the middle of it, this entire iron core does not connect this coil to this coil electrically. There's no electrical connection between this coil and this coil. The only thing that connects the primary coil to the secondary coil is a magnetic field. So the magnetic field, so remember, anytime you have a current moving through a wire, especially a current moving through a coil of wire like this, it behaves as if it's a bar magnet. So there would be a north pole at the top and then a south pole at the bottom. But the thing, since this is an AC power supply, In the next instant, the current would be going the other way. It would be going this way, which means then all of a sudden there'd be a south at the top and then a north at the bottom. And then 1/60th of a second later, that would switch again. And there'd be a north and then a south. And it just keeps on switching back and forth to a north, south, south, north, north, south, south, north, constantly. So the thing is, remember that a coil of wire, when it has a current going through it, it has a magnetic field pattern just like a bar magnet would. So this would have, if it weren't for this, let's just kind of get rid of this this iron core for 1 second. Let's just pretend that we just have, actually forget all this, let's just pretend we have just a coil of wire. Okay, we just have this coil of wire and we have AC current going through this coil of wire. Okay, if that were the case, the magnetic field around this coil of wire would look something like, ooh, that's a little thick. It would look something like, let me get rid of this first. So if we had a current going through this coil of wire, it would have a magnetic field around it that looked just like, just like this. You know, just the same as a bar magnet, right? So this is the same shape of a magnetic field there would be around. If you just had a bar magnet with a north and a south, it would have a magnetic field around it that looks just like that, right? Okay, so this magnetic field around the solenoid that has a current through it is just the same as this magnetic field, just the same shape as this bar magnet. Okay? Now, did you see how spread out that magnetic field was? The purpose of this iron core is to take all of the magnetic field lines that come out of this primary coil, and basically it just focuses them all through the secondary coil. So all of the field lines that come out of this primary coil, instead of just kind of going off into the air, this iron core makes sure that they all pass through the secondary coil. That is the function of the iron core. All the field lines produced around this primary coil just get focused right through the secondary coil. That's the purpose of the iron core. So now let's take a look at our secondary coil. So this secondary coil has a constantly changing magnetic field, because just as this was going north-south and then it was south-north, because this magnetic field is altering, then this magnetic field is also altering. There's a north and then a south here, and then a south and a north, and then back to a north and a south. So the magnetic field from this coil gets sent through here, through the secondary coil, but it's constantly changing. The magnetic field is constantly changing because of this AC power supply. That means there's a constantly changing magnetic field inside of this secondary coil. Now, what happens when you have a changing magnetic field in a secondary coil? It induces a current, and that's where the current comes from in our secondary coil. That's where the current comes from to light up this lamp, because the magnetic field is alternating, it's constantly changing, meaning this secondary coil is constantly cutting field lines, meaning there's a constantly induced alternating current in your secondary coil. And essentially, that's how a transformer works. Now, I want to mention one more very important thing about transformers. You can see on this primary coil, there are how many turns of wire? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who knows? About maybe 14 turns of wire. On our secondary coil, we have 1, 2, 3, 4, 5, 6, 7. Only half. So we can see on our secondary coil, we have only half as many turns as our primary coil, which means that this transformer would be a step down transformer, meaning if there's half as many turns on the secondary coil as there are on the primary coil, that means it would turn, if this were a 240 volt input, that means it would turn it into 120 volts. It's a step down transformer. But the thing is, if this was 240 volts down to 120, what happens to all that other energy? Well, the thing is, if this was 240 volts, let's just say it was 1 amp. of current, 1 amp of alternating current. Because this 240 got cut in half down to 120, that means the current would double. So it would turn into 2 amps. Because remember, transformers obey the law of conservation of energy. So let's see, how much power? P equals IV. This would be 2, so I is 1 amp, V is 240 volts, 1 times 2. So this is 240 watts of power. What do we have over here? Well, let's see, for a secondary coil, P equals IV. I, in this case, is 2 amps, and V is 120. Again, 240 volts. So basically, the power for what's called an ideal transformer will always, sorry, I said volts, I meant to say watts, 240 watts of power. So for an ideal transformer, which is all you'll ever see, almost, the power has to remain the same. That just means if your voltage gets halved because you're using a step-down transformer, then the current would have to be doubled. That's all it says, because the power, well, the energy and therefore the power has to remain the same. You cannot create energy, you cannot destroy energy. And this is assuming that we're not losing any to resistance or anything. That's a 100% efficient transformer. Okay, so let's move on from there then. Okay, so this is basically everything we've just said. Let's move down. So how do transformers work? So here's another image of a transformer. And basically all of this writing is stuff that we've already said here. The primary coil must be connected to an AC power supply. Okay, one thing I want to kind of stress again is what it says down here. No wires connect the two coils. There is no electrical connection between this coil of wire and this coil of wire. The only connection between this primary coil and this secondary coil is via the magnetic field that gets focused through the secondary coil from the primary coil. That is the only thing connecting these two coils, is the magnetic field produced by the primary goes all right through the secondary. That is what connects these two things. There is no wire connecting these two magnetic fields. And this iron core does not conduct electricity from your primary to your secondary coil. This iron core's sole purpose is to focus all the field lines from your primary into your secondary coil. That's the only purpose of it. It is not an electrical connection between the primary coil and the secondary coil, which means all of these wires would be insulated. So there's no electrical contact between these wires and the iron core, or between these wires and the iron core. Again, the only thing connecting these two coils of wire is the magnetic field. That's what's transferring the energy. It's the magnetic field that is transferring the energy from the primary coil to the secondary coil. And just as a little side note here, you can see that our primary coil in this case has 1, 2, 3, 4, 5, 6 turns of wire, but you can see our secondary coil has many more turns of wire, meaning this one would be a step-up transformer. It would turn a small voltage into a bigger voltage. More on that in just a little bit here. Okay, and so all of this stuff is stuff that we've already said, so you can go through this presentation on your own a little bit later. Okay, so here's something we've already mentioned also. Transformers can be either step up or step down. So here's another example of a step-up transformer. So notice a step-up transformer has more turns of wire on the secondary than the primary. It's stepping up. So this would go from something, for example, 100 volts on the primary. It would turn that into 400 volts on the secondary. So that would mean that there's 4 times as many turns on the secondary than there are on the primary wire. So let's see, to go from 100 to 400, that's times 4. That means the current would be divided by 4 because power remains the same. So that means 10 divided by 4 gives you 2.5. And that's it, because on this side we have 1,000 watts, current times voltage. 10 times 100 is 1,000. And same thing over here. Power is 1,000 watts, current times voltage. So 2.5 times 400 is 1,000. So in an ideal transformer, the power remains the same between the primary coil and the secondary coil. It's the current and the voltage that get changed around. And if the current goes up, the voltage goes down. If the current goes down, the voltage goes up, and vice versa. So step-up transformers are used to increase the voltage. They have more turns on the secondary coil. And then a step-down transformer is used to decrease the voltage, and they have more turns on the primary coil. So you're going from many turns down to just a few. It's a step-down transformer. So this would reduce the voltage. And just notice here, we are turning 1,000 volts. 1,000 volts is getting turned into 200 volts. So we are dividing by 5. And now just look, 2 amps gets turned into 10 amps. And that is times 5. So that we have 2,000 watts of power on the primary, because 2 times 1,000 is 2,000. And 2,000 watts on the secondary, because 10 times 200 is also 2,000. So the power remains the same. If the voltage gets decreased, the current gets increased by the same factor. Moving along. So now there's actually an equation you can use to calculate that. So what I've just shown you is actually the easy way of doing it. The easy way is just to say, well, what's happening to the voltage? Oh, the voltage is divided by 5. That means the current is going to be times 5. Simple. That's probably the simplest way to look at it. There is also, however, an equation you can use, and that is the transformer equation, which just looks like this. And this just means the voltage of the primary divided by the voltage of the secondary is equal to the number of turns on the primary divided by the number of turns on the secondary. So in any question, you will have one of these that's unknown. Maybe it's the voltage of the secondary. And you would just have to rearrange this to solve for that. Or you can just look at the short way of doing it, which I showed you earlier, whichever you prefer. Oops, okay. So now, again, we've mentioned this too. If voltage goes up, then current goes down because the power remains the same, and that's assuming that we have a 100% efficient transformer. And that is what it will be in most cases on tests. Okay, so this is just what we've already said before. So power remains the same. That means power on the primary is going to be equal to the power on your secondary. And we know that to calculate power, it's equal to power is equal to current times voltage. So this just means that the current times voltage on your primary is equal to the current times voltage on your secondary. And so one of these might be an unknown. Maybe it's the voltage on the secondary that you need to solve for. In that case, all you would have to do is rearrange this equation and say that, well, the voltage on the secondary would just be the current on the primary times the voltage on the primary divided by the current on the secondary. Maybe. Who knows what you'd have to be solving for, but it's very simple. Okay. Next. Here is just an exam-style question, a very typical structured question on transformers. And it just says, Figure 9.1 shows two separate coils of wire wound around an iron core. So there's just a transformer. We can see here there's more turns of coil on the primary than there are on the secondary. So already this looks like a step-down transformer. But I don't think that's what the question's getting at. The question is just saying, explain why there's a current in the lamp. So why is there a current in this lamp right here? Because this secondary coil does not have a power supply to it. How is it getting electricity to this lamp? Well, what do you think you'd have to say? Well, let's just talk about it first. Remember, we haven't, so this little symbol right? This little squiggly line that looks like a squiggly line, that just means that this is an AC power supply. Remember, transformers have to have an AC power supply in order to work. So remember, we have this AC power supply, which means that we have an alternating current in the primary coil. That alternating current in the primary coil creates an alternating magnetic field in the secondary coil, which is constantly changing. So that alternating magnetic field around the primary coil gets focused into the secondary coil by the iron core. And now this alternating magnetic field in the secondary coil induces an alternating current in the secondary coil. And that alternating current in the secondary coil ends up lighting up this lamp, and that answers the question. So what would we be writing down to answer this question? Explain why there's a current in the lamp. Well, you'd say something about, let me just change this thickness. Say something about alternating current in the primary coil. Alternating current primary coil produces alternating magnetic field. Produces an alternating magnetic field in the primary coil. And then you'd say something about the iron core focuses the magnetic field. That iron core focuses the magnetic field into the secondary coil. So that's point 2. Point 3 is the alternating magnetic field in the secondary coil induces an alternating current. So I'll just write alternating magnetic field in secondary. The important word here is induces an AC current in the secondary. Okay, so let's see how many marks we would get for this answer. Oh, I'm going to have to move this over. Let's see, I might have to erase this. So let's see the answer now. Here's the mark scheme just beneath it. If I'm able to move this over. Okay, so here's the mark scheme, which says alternating current. So alternating current in the primary. So basically any mention of the magnetic field in the iron core gets 1 mark. Any mention that the magnetic field is alternating is another mark. So that's produced because of the primary coil. So the field cuts, or the field links with a secondary coil, or the secondary coil cuts the field lines. So that magnetic field is focused into the secondary coil. This secondary coil is cutting the magnetic field lines, and that induces, so see how that's bolded, the word induce? You have to use that word. So that changing magnet, or because the secondary coil is cutting field lines, that induces an EMF or a current in the secondary coil, which contains the lamp. So it's all there. I'll leave that uncovered so you can see it when you look at the presentation yourself. And then one last thing to mention in transformers is power loss in cables. Now, these are very common questions and past paper questions. So the question is, how do they minimize the power loss in transmission cables? So the thing is, when they produce electricity at a power generating station, it's usually produced somewhere very far away. So in order to get it to the cities like KL, they have to have the electricity run through these super long power cables that go for hundreds of kilometers. And the thing is, when you have wires going for hundreds of kilometers, you're going to have some power loss. They're going to lose energy. They're just going to, an electric current produces some heat, and that heat just gets wasted. So how do we minimize that wasted energy, that wasted heat? Well, what do? How do they minimize it? They step up the voltage to a very high value. Now, why would they make the voltage? They make the voltage in these cables super high. Like this could be in the hundreds of thousands, almost 1,000,000 volts. So hundreds of thousands of volts. What's the reason that they do that? They do that in order to make the current super low, because it's the current running into resistance that wastes energy as heat. So they step up the voltage to a very high value in order to decrease the current to a very low value in order to reduce the heat loss by the current encountering resistance in the cables, because you can't have a perfect conductor. Every cable has some resistance to it. So it's that current running into resistance which wastes energy as heat. So let's see what we've written here. So how do they minimize power loss? They step up the voltage to a very high value. Why do they do that? So by increasing the voltage, you decrease the current. And power loss is due to a combination of current and resistance. Since we can't change the resistance of the cable, the resistance of these wires is set. That just depends on the material that they're made of, copper in this case. And so since we can't change the resistance, we minimize the current. So it's all about minimizing the current to minimize the power loss. And the thing is, power and current are related, and resistance are related by this equation, P equals I squared R. So this just shows you, so basically, the higher the current, the higher the power loss. So you want to make this current as small as possible. You want to make that current very, very small so that the power loss is also very, very small. So how do you do that? You make the voltage very, very high, and then the current is very, very low, and you're minimizing power loss. Now, okay, just a little note here. So why do they want to do that? Why do they want to reduce power loss? Well, the biggest reason is money savings. You don't want to waste electricity. You want to sell electricity and turn it into money. So using high voltage and low current allows, well, there's a few things. Not only does it minimize power loss, but it also allows you to use smaller cables because you don't have a large current. If you had a large current, you'd need large cables. So we have small current, so that allows them to use smaller cables. And when you're running cables for hundreds and hundreds of kilometers, having them a little smaller will save you a lot of money in the long run. So the thickness of the cable is dependent on the current in it. So if you have a very small current, you can have a very small cable. And smaller current means smaller wires, which means money savings. And that is the end of that. I believe, let's just make sure this is the end of the presentation, and it is. So I hope that this was helpful for everybody. I hope that made sense to you. And I will put some quizzes online, some multiple choice questions and some structured questions, and then we'll go over all those when we have our next online video lessons together. So I hope that was helpful. I hope you all enjoyed it, and we'll see you soon.